Hello everyone, and welcome to my video on estimating the area under a graph, part of the integration series for mathematical methods units 1 and 2. Now don't worry if you don't know what that means. Integration is integration. It's part of calculus, and it is an amazing subject that hopefully I'm going to give you a flavour of now. My name is Darren from Maths Guru. Thank you very much for joining me. Great to see you. And as you can see behind me, there are our learning objectives. And basically by the end of this, we're going to look at what the left endpoint method, the right endpoint method, and the trapezoidal estimate are going to be used for to help us find areas under curves. All right, now this is really an approximation and it leads into something much bigger in the next couple of videos. But I think the basic understanding that's needed through this video is going to be significantly helpful. And I've seen this come up on tests and SACs all the time anyway. Now, before I go much further, do me a massive favor if you can and subscribe to my YouTube channel. Why? Because who watches maths videos? The fact you're watching this at the moment probably means you've been made to, or you really have no life like me. So actually clicking that subscribe button does two things. Number one, it makes you feel good. No, it makes me know that someone out there has watched my content. Right, recap of past learning. Now, as this is the first lesson, how on earth can there be any past learning? Well, actually, it's going to build on something that you did in year 7 and probably year 6 and maybe even year 5. What? Well, finding the area of basic shapes. Now, we know that we can, using mathematics, find the area of squares and trapeziums and circles and triangles and all those type of things. Now, there are basic building block shapes. What we then do is we can put them together and we find composite shapes, and that would have been the next section of the course, and we build up harder and harder and harder. And then obviously when we get to mathematical methods, we sort of go all this conceptual stuff. But actually today we are going to go back to the idea of finding areas of rectangles and trapeziums. Now, for those of you who do not remember the area of a trapezium, that is the gross formula, and everyone out there seems to love formulas. I don't, because what I do is say, well, we add the parallels, multiply by how far apart they go, and divide by 2. No, I haven't had some sort of mental break. That's exactly how I teach it. Add the parallels, times by how far apart they are, and divide by 2. Happy? Okay. Rushing ahead a bit, let's go back to something nice and simple first. Now, this is the base function I'm going to use throughout the course, and my videos are mapped against the Cambridge Mathematics series. Thank you very much, Cambridge, for letting me use your examples. You guys absolutely rock. All right, so there we go. So this is the function we're going to do here, which is 9 minus 0.1 x squared. And we're actually going to just limit that between the domain of 0 and just below 10. I don't want to look at the whole graph here. And this is what we're going to do. We're going to try and find the area between or under part of that curve. Now, realistically, in real life, that doesn't make a huge amount of sense. Or does it? Why would we want to find the area between two sections of a curve? That comes up in a later video. But at the moment, we're going to look at the idea of what if I needed to find the area between, say, that point there and that point there, and I just want to find this area under here at this moment in time. Okay, well, we got the basics. Well, we could use rectangles. That seems to make sense. Yes, we know how to find the area of a rectangle. So what if we could draw a series of rectangles starting at our first point, and here the question says, what we're going to do is we're going to find the area between two limits. And those limits are always given as x equals. They're always given as vertical lines running through a coordinate position or position on the x-axis. So in this situation, it says we're going to find the area under the curve between x equals 2, which is that line there, and x equals 5 there. Now, using rectangles, there are actually two ways of doing this. We're going to use or look initially at the idea called the left endpoint estimate. Now, what that means is when we draw our rectangles, we're actually going to have the endpoint, the left endpoint of the rectangle. And by that, I mean here is my rectangle and there is my left endpoint, just there. Oh, can you guess where my right endpoint is going to be? Yeah, that's going to be my right endpoint there. So we're going to draw it such that we can have our left endpoint just touching the curve for each of my rectangles. Oh, awesome. Now, I suppose the next question is, how do you find the area of a rectangle? Oh, how do you find the area of a rectangle? Well, it's base times height. Yeah, or find a right angle and multiply those two together. Oh, well, what we probably need to do is make our life a little bit easier. And what I'm going to do is I'm going to choose rectangles that all have the same width. Believe it or not, later on that's going to make my calculations a little bit easier. So there's one width, and there's another, there's another, there's another. And it turns out the width of each of these rectangles is going to be half. Why did I choose half? It seemed as good a value as any. If I was to choose one, we'll see why that's going to be a bit of an issue in a moment. If I chose smaller rectangles, it just means a lot of calculations. So at the moment, we're choosing a half as my width. So I now know each of these rectangles is a half. All I need to do now is find the height of my rectangle. How do I find the heights of each of these rectangles? Yes, because what we notice is that the left endpoint touches that graph there, or it touches the curve, doesn't it? And do I have a way of finding that coordinate position? Well, yes, of course we do, because what we know is that we've got a function, and every point on that function is 9 minus 0.1 x squared. Well, for this point here, I know that x is equal to 2. So how could I find the height? Well, I could fire up my calculator, yes? So if I fire up my calculator, and I'm going to use the TI Inspire. Guys, for the class pad, you have pretty much the same functionality. So I'm going to hit menu, I'm going to do a calculator, please, and I'm going to do 9 minus 0.1 times 2 to the power of 2. Hit enter, and there we go. Yuck, that's horrible. So what I'm going to do is I'm actually going to copy that down and do as a decimal at this moment in time. So 8.6 is the height of that rectangle there. Oh, cool. So now, if I was to do 8.6 times 0.5 and hit enter, I get 4.3. I now know the area of that rectangle there is 4.3. Yay! Can I do the same with the next rectangle? Well, of course I can. But I've got to now work out the new left endpoint, because this height is different from that height. So this left endpoint is going to be when x is equal to 2.5. Okay, so I now know that there, x is equal to 2.5. What's my y value going to be? Well, to make life a little bit easier for me, I can define f of x equals 9 minus 0.1 times x squared. Come on, you can do this. X squared, hit enter. And now if I just do f of 2.5, hit enter, and again, let's turn that into, I get 8.375. So 8.375. Cool. Can I find the area of that rectangle now? Yes, because I'm just going to do that value there and times it by 0.5, and that's going to give me 4.1875. So there we go. We got the area of that one there is 4.1875. And so you go on. And basically, that is one of the ways of finding the estimate of the area under that section of the graph. Simply finding the area of that rectangle, and adding them all together. Now, do you see the problem? Well, I'm going to skip onto a slide for just a moment, because actually that's not going to give me a particularly good estimate, is it? Why? Well, what do you notice about all of these sections at the top of my boxes? They're actually above the curve, which means that we're ultimately then going to end up with an overestimate. Yeah, because all these tiny little areas up here are actually going to add on. It's going to give me an area that's way too high. So what can I actually do? All right, well, let's consider a section called the right endpoint estimate. Now, what is the right endpoint estimate? Well, pretty much as I said just a moment ago, here we notice that for each of these rectangles, it is the right point of the rectangle that is actually going to give me the height of that rectangle. We notice we've got, once again, my widths here are 0.5. Yep, I've got my widths of 0.5, but what do I need to do? Well, I work out my height of my rectangle. And this is what sort of confuses people, because weirdly, they will then go and put 2 back into my function, but actually, that's not the height of that rectangle, right? The height of that rectangle in this situation is 2.5. But we've already worked that out, haven't we? Because if I go back to my calculator and f of 2.5, we know that's 8.375. So the height of this rectangle here is 8.375 by 0.5, put it into my calculator, and we're going to come out with 4.1875. 0.1875. And again, you just repeat the process. Now, if I go back to this diagram here, well, obviously what I've done here with Desmos is I've put on my coordinates already. I've actually got my calculator to work out my heights and my coordinates already for me. So in this situation here, that coordinate there was only going to use for my left endpoint estimate. This one here would also be used for my left endpoint estimate, but for the second rectangle, the third rectangle, the fourth rectangle. But if I'm doing the right endpoint estimate, I don't actually use that one there. I use this, I use this, and I use this. Now, just to give you a bit of a shortcut on how to properly do this on your calculator, if I actually go and do Control, insert a list and spreadsheet. Now, what I'm going to put here is I'm going to put my X values. I'm going to 2, 2.53, 3.5, 4, 4.5, and 5, I think was my other value. Now, because I want it actually to be in decimals, I'm going to go settings. He says every single time my calculator gets a little bit overexcited. Document settings, I'm actually going to change from exact to approximate just to make life a little bit easier. Right, here, I'm going to put f of x. I can't put that, so I'm going to put height. Now, the reason I can't put f of x is because it came up in bold, so that's not particularly helpful. When I go to my second line here, the one that's currently highlighted, then what I see is a formula. I can put in a formula. Now, we know that that was 9 minus 0.1 times. Now, when I hit x, you'll notice there's a bit of a problem because your calculator at this moment in time doesn't know what that x value is going to be. And so actually we use the var keyword down here, and then I want to choose x, and I'm going to do squared and hit enter. And lo and behold, what do we notice here? Well, we now notice that we end up with our individual heights. So if I go back to my diagram, what I've got here, 2.5 is 8.375. There we go, 2.5 is 8.375. If I put 2 in, I get 8.6. So there's my 2 is 8.6. And I think I highlighted them the wrong way around a moment ago, but that's okay. We get the general idea. So now actually I've got my calculator to work out all the heights of my bars. All I've got to do is make sure that I use those in my correct calculations to help me find the areas of each of those boxes. All right, now again, do you see the next problem? Because if I use the right endpoint estimate, is it going to be accurate? No, not again. And actually what we see here is that now it's going to be an underestimate because we've got all these little areas under here that's going to cause an underestimate. So if I go back again to this one here and I talk about the widths again, do you see what would happen if I actually made my widths or my intervals 1 unit? Well, this would actually go all the way across here and down there. This one would go all the way across there, and that would go all the way across there. And so with a much wider bar, we're actually going to end up with a much bigger overestimate. Ah, well, if that's the case, and I've got an overestimate with really wide bars, could I make my bars narrower? Well, I could do. And absolutely, if I was to make these bars rather than 0.5, 0.25, then our estimate would actually be a lot closer to the actual value. So a natural extension seems to be that what would happen if I made the width of my bars narrower and narrower and narrower and narrower and narrower? Well, we'd get closer and closer and closer and closer to the actual area under that curve. And that sort of leapfrogs on a little bit later on into sort of what integration actually is. But for now, for this particular section of the course, you're not going to make these too small, otherwise you will be here forever trying to work out the individual areas. Now, it would sort of make sense that if you wanted a more accurate version of the area under the curve, then one of the things we could do is we could actually take the area of the right endpoint method. We could take the area we got for the left endpoint method, because one's an overestimate and one's an underestimate, add them together and divide by 2, and then we end up with 23.145. Now, actually, using the work that's coming up in a later video, I can find the actual area under the curve between x equals 2 and x equals 5 to be 23.1. Now, actually, That would suggest then that adding these left endpoint and right endpoint estimates together and dividing by 2 is probably a lot more accurate than actually we would get by here. Is there another way we can make it even more accurate? Well, if we go back to my introduction, what did we turn around and say? There were shapes that we could use, and I sort of labored one. There we go. We could use a trapezium. So actually, there is a way of using a trapezium. But before we jump onto that, let's look at an example. All right, find the sum of the areas of the shaded rectangles to approximate the area under the graph of that between x equals 0 and x equals 3. Okay, so x equals 0 and x equals 3. So let's make sure we've understood. So there and there. Lovely. Now, what do we notice? Are we using the right endpoint method or the left endpoint method? Well, it says here it seems to be the right endpoint method. So let's see what we've actually got here. We've got this rectangle here, which is going to give me a right endpoint method of 0.5. So I'm basically going to do the function of 0.5. Now again, what does that give me? That gives me this height here times 0.5. And I'm going to add that to what? Well, I now want the function of here, which is the function of 1 times 0.5 plus the function of 1.5 times 0.5 plus the function of 2 times 0.5 plus the function of 2.5 times 0.5 plus the function of 3 times 0.5. Now again, there's a lot of stuff in there, isn't there? But if we were to now use our basic algebra, what I can actually do is I could take all of these times 0.5s out of a set of brackets, and therefore I would end up with a half of f of 0.5, he says right in 0.3, plus the f of 1, plus the f of 1.5, and all the way up to the function of 3. And actually, that's what I'm going to do using my calculator now. So if I bring up my calculator, which I know is going to cover my screen, let's not use that any moment. I'm now going to redefine. I'm going to define f of x is equal to, now it's come up as bold, but that's all right because I'm effectively going to, now what do you notice here? And these are the great things about using a calculator and learning all the things that might trip you up. Well, I've got a problem. I've got an f of x already defined, okay? But that's not a problem because I'm just about to redefine the function. But I actually have x already defined as well. So what I need to do is either shut down my calculator and start again, or, well, actually, I'm going to have to do that because I've got a list and spreadsheet here with x in it. So what I'm going to do is I'm going to go Control and up, and then I'm going to delete that one. And then click back to problem 1. I'm just going to see what this does now. Define f of x, we already know that, is equal to x. Right, your calculator still thinks it's got stuff in memory, but what I can do now is I can actually go Menu, Actions, delete a variable, and I'm going to hit x. Now when I hit x now, you'll notice it's just a normal letter. So we're going to define f of x equals x minus 2, x plus 2, and then x minus 1 all squared plus 10. Now, a lot of people realize that this is actually incredibly soul destroying. Doing this takes a long time. And what value is there? I'm not overly sure, all right? So would you be expected to do lots and lots of this? Probably not, but it's one of those things I have seen in tests altogether. So there's my f of x. So now what I'm going to do is I'm going to do a half times, oops, he says not doing times, f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. His fingers aren't working very well today. Plus f of 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now what I really did there was just make sure that I had 6 heights. And then when I hit enter together, I don't know what just happened there. I managed to drag and drop. Hit enter, and there we go. So my estimate there, and it's going to be an overestimate. In fact, it's going to be quite a massive overestimate probably, because if you look at the bars here, they seem to be sticking out quite far, particularly this one. That's huge. But an overestimate is going to be for that one there. 41.84. He says handwriting is really bad today. 41.84. units squared. Now I always write the unit squared because it is an area. But what it does go on to say is when we use the left endpoint method for exactly the same interval, what we find out here is the area comes out to be 29.84375. And the actual area of the graph is going to give 35.1. So what I'm going to do is add together the 29.84375, add it to my value that I got earlier, which was 41. So let's just copy that down, hit enter, divide by 2, and see what happens. There we go, 35.8. Much, much closer when we do all of those. So just keep that in memory that if you were ever going to do this and you wanted a closer approximation, do the left endpoint estimate, then the right endpoint estimate, and add them all together. Now, I just want to turn around and say, for those of you who want to know how to do the left endpoint much, much quicker, well, really, all we're going to do is knock off this last height here and just add on f of 0 here. Now, if I've done this correctly, I'm going to get, there you go, 29.84375. So a useful thing there that actually, once you've defined your function and you know which x values you need, the rest of it becomes fairly trivial. All right, but how do we find the exact area? Well, that's coming a bit later on. But here's another example with the trapezoidal estimate. Now, what is a trapezium? Now, trapezium is you add the two parallels together, multiply by how far the parallels are, and then you divide by 2. So let's just talk over the general idea of this at this moment in time, because what we're now saying is to find the area of this trapezium, we add the parallels together, you multiply the distance, and divide by 2. So if we were going to find the area of that first trapezium, we would therefore do a half. Oh, that's an awful color. My daughter's been playing with my iPad, so I'm just going to stick to black at the moment and change all the colors because she's now got everything like white, light gray, light pink. Not going to work. So let's go back to find the trapezium T1. So that would be a half times, all right, because the area of a trapezium is a half times, add the parallels, and by how far apart they are. So a half times f of 2 plus f of 2.5, they should be in brackets, times the width, which is going to be a half. So that's a half times a half in this situation would give me a quarter. So let's make that a quarter times f2 plus f2.5. Okay. What about the next one? What about the next trapezium? So this would be T1. What about T2? Well, that's once again going to be a half times f of 2.5 plus f of 3 times a half. Well, that half times a half is once again going to give me a quarter. And what we start to see was if I was to combine these together, all right? If I was to now combine these together, I could take a factor of a quarter out of both of those. And I know this is only for 2 sections, but I could take a quarter out of those and I'd end up with f of 2 plus f of 2.5 plus f of 2.5 plus f of 3. Hold on. That can be simplified. That would be a quarter of f of 2 plus 2 lots of f of 2.5 plus f of 3. Now, if I was to continue doing this, and I urge you to do it just to work out the maths behind it, what we find out is to do the trapezium rule, actually life is much, much easier if we think about it in a slightly different way. First things first, this a half times whatever your width is going to be common to everything. So we can work out this value outside that bracket. It's nice and easy. It's going to be a half times whatever your width is here. We know that this one here, f2, is only ever going to be used once. Likewise, f of 5 is only ever going to be used once. But we know that this bar here, this height here, is actually used twice. We've already worked it out here. F of 2.5 is part of this bar here, and it's that bar there. But what about f of 3? Would I use that more than once? Well, yes, because it'd be part of this bar and it'd be part of that bar. And f of 3.5 and f of 4 and f of 4.5 would be used twice. So actually, we can work this out by saying, well, we want the function of the first bar, the function of the second bar, and basically 2 functions of every bar in between. Now, hopefully that's sort of making sense. If not, go away and practice because it makes life so much easier. It's actually awesome, yes? So if I wanted to do this, let's actually now, I'm going to do the maths behind it. So therefore, if I wanted to find the area of this, I'd be a half times a half, lots of, and we would say f of 2 plus 2 lots of f of 2.5 plus 2 lots of f of 3 plus 2 lots of f of 3.5 plus 2 lots of f of 4 plus 2 lots of, let's do that again, 2 lots of f of 4.5 and only 1 lot of f of 5. And basically, if I put that into my calculator, he says, I'm not really wanting to do this, but in for a penny, in for a pound. And I'm going to do 1/4 times, right, we got f of 2. First things first I've got to do is actually go back and redefine my function because I've gone back to my original. So let's define f of x back to being 9 minus 0.1 x squared. There we go. Right, so if I now do 1/4 times f of 2 plus 2 lots of f of 2.5 plus 2 lots of f of 3 plus 2 lots of f of 3.5 plus 2 lots of f of 4. That does not sound good, does it? 2 lots of f of 4.5 plus 1 lot of f of 5. Right. Now again, I always go back and just check that I've got these right. I've got 5, 4.54, 3.53, 2.5, and just 1 lot of 2. Hit enter, and there we go. Out comes a estimate as 23.0875. Now, bearing in mind, we knew from a previous part of the video that that was actually an estimate of 23.1. We can see that that's actually much, much closer. And if we rounded that to 1 decimal place, then we'd be pretty sorted there. Okay, now we've just done that example, I think. Am I going to do that one again? Nope. Now, there we go. There is a formula for those of you who like them. I hate formulas at the best of times. I'd much prefer to sort of work things out using the theory I just before. But if you wanted to use a shortcut for the left endpoint estimate, basically it's given by b minus a. Now, in this situation, b is your end value of x, a is your start value of x, n is the number of divisions you've got, and there you basically f of each of the individual a, x1, x2, x3. Right endpoint method given by here, and trapezium is given by here. Again, I'm not sure that I necessarily want to learn a number of formulas, but this is really what I've just been talking about a moment ago. There we go. We're almost at the end of the video. Did we talk about the left endpoint method? I did. The right endpoint estimate? Yes. And trapezoidal estimate? We have done. Okay, so there we go. That is a way to estimate the area under a course. If you can subscribe, under a course, under a curve. If you can subscribe to my YouTube channel, that would be massive. Thank you very much. Spread the word about these videos. They are out there trying to help you as much as I possibly can. There are more videos coming. Hopefully, I'll see you in one of those. If not, please take care and stay safe. Bye-bye.